Hello and welcome to Beamer, folks. Okay, before I continue, I'll just summarise the modifications I kind of learnt on the way of this journey. First of all, we'll have a look at the sync circuit, and all I've really included here is the R null balancing resistor of 39k. That seemed to be about the best value for this particular op-amp here. Other op-amps you might need to change that very slightly to balance the difference between 0.96 of a volt DC here at the junction of R2 and R3 and the output voltage as across R5, which is the 100R. And that's about it as far as the sync circuit is concerned. I'll move up to the source circuit, and you can see that there's been slightly more alterations to this. One is, again, I've included this null balancing resistor here, but more importantly, I've included the two power supply dropping diodes D10 and D11, establishing a 1.5 volt lift on the positive side, that's pin 8, positive side of the op-amp, to the supply input. And as you notice here, the supply input has I've lifted to 13.5, allowing for the 1.5 drop across there, which produces a compliance voltage of plus 12 volts. Okay, so that's the sync and the source as applied to Darlington pairs. Now, my next progression here is I move on to the sync circuit utilizing a MOSFET, an N-channel MOSFET, and we see how that goes. And that is this circuit C here. It's virtually identical to the Darlington pair, except it's slightly simpler, and you can see that the gate of the MOSFET is attached to pin 1, which is the output of the op-amp, and then you've got a drain, which is the output to the load, and then you've got the source, which is connected to the 100R. And this is what I've got to implement next. Okay, I've taken us back to the sync circuit for a couple of measurements before I move on to the N-channel MOSFET. One of the parameters I wanted to measure, I've set across R5 a voltage of 0.1 of a volt, as you can see there on the meter. That will of course produce 1 milliamp in the LED load, but so having set that at 0.1 of a volt across R5, I wanted to take a measurement on the output pin, which is pin 1, and see what voltage above 0.1 of a volt is driving Q3, the base of Q3. Now I just move, as you can see, it's at 0.1 of a volt there across R5. Oh, my meter's playing up. Okay, let's try that. Let me just move that across to there. And you can see, and I'm going to make a note of this, so for the Darlington pair, Q3 and Q4, the voltage driving at the base of Q3 is coming out at 1.23 volts, and that's including 0.1 of a volt across R5. If you make R5 as low as possible, at the moment it's 100R, if you make it as low as possible, you don't need so much voltage across R5 to achieve the current, the desired current. The second parameter I wanted to measure is just see whether how much current is flowing through the LED. So what I'm going to do is short them out. I've moved my meter over to the current range. I've got 6 milliamps FSD, full scale deflection, and I'm going to short out the LED to find out what current it is. It's 1.014. Okay, and that's that. Now I'll move on to the MOSFET and see how that performs. I've disconnected the Darlington pair and connected in the N-channel MOSFET IRF540. The source of the MOSFET goes to R5, and I've just adjusted the potentiometer for approximately, again, 0.1 of a volt across R5. And the parameter I'm interested in, the same as the Darlington pair, is the output of IC3, which is pin 1, and I've got my, I'm going to move my voltmeter through to that pin. And for that 0.1 of a volt across R5, I'm now reading on pin 1, which is the output of the op-amp, as you can see there, 2.649 volts. And a MOSFET, whilst it's got very good parameters in all other respects, although leakage current can be a problem, the one disadvantage it's got is that it takes quite a bit of voltage on its gate for it to start conducting between its drain and source. This does not improve for increasing the current through the MOSFET, and unless you specifically select perhaps a DIRA MOSFET, which has a low voltage gate drive, if you're not careful, it requires 4, 5, maybe 8 volts to drive a MOSFET into reasonable currentage conduction. The thing that I'm looking at here is one of the things that I wanted to do was make sure that this current sink and source can operate down to a very low voltage. And what I mean by a low voltage, the op-amp itself is designed to go down to 5 volts. I'm hoping to get even slightly lower than that. And if you've got a driving voltage above 0.1 of a volt across R5, because don't forget the 0.1 of a volt is added to the drive voltage, it will exceed the voltage of a low supply. And so therefore I tend to favour the Darlington pair. Although it's got its disadvantages, the one thing it can do is go down to a low voltage. If you remember, the Darlington pair, 4.1 of a volt across R5, only needed 1.23 volts DC, whereas even with just 1 milliamp through the conduction of the MOSFET, I'm needing over twice that amount of voltage, 2.649. So for low voltage use, I don't hold much faith in the MOSFET, certainly the IRF540. If one could choose the particular MOSFET ideally suited to this, it would probably turn out to be quite an expensive device for low voltage use. Of course, the other parameter I was interested in, was the current through the LED. 4.1 volt across R5, and I do the same test for the for this MOSFET. Now let me short out, always a tricky business shorting things out. Let me short and make sure I've got my correct current range, which I have. Let's short out the LED and see what current's going through it. 1.033 milliamps. So it's 33 microamps above 1 milliamp. Okay. The reason why I did that last output current test, which was identical to the Darlington pair, was I was trying to determine whether there's any disturbance in the linearity between the N-channel MOSFET and the Darlington pair. I made a note of the numbers, and the Darlington pair across R5 was 0.101 of a volt, which produced 1.014 milliamps. The N-channel MOSFET across R5 was 0.103 volts DC, and the current through the LED was 1.033 milliamps. Well, it looks as though there is a current disturbance in the N-channel MOSFET circuit of 3 microamps. There's a difference of 3 microamps there. With the Darlington pair, the difference was 4 microamps. So it looks as though if there's a disturbance at all in the linearity, it could probably rest in the Darlington pair. But as it is only 1 microamp, and this is not an ultra precision reference instrument, I think it's perfectly acceptable. It's certainly something I'm prepared to trade off. This is Beamer signing out for now.